Welcome back. In this section, we'll be talking about solving various kinds of equations. Equations involving radicals, equations that could be rewritten as quadratic equations, and also some other sorts of problems that involve some clever factoring. So, to begin with, talking about radical equations, any equation that has a root in it, a radical expression, is a radical equation. Now, of course, I'm not really talking about equations so much where there's a number inside of the square root. I'm talking really more about equations where there's expressions involving a variable inside that square root. So, the idea is that if you're looking to solve a radical equation, start off by isolating one of those radicals. Now, it doesn't have to be necessarily square roots. It could be cube roots or fourth roots. Typically, we'll see square roots. But depending on whatever the kind of root you have, that's the kind of power you'll need to raise both sides of the equation to. So if we have a square root equal to a bunch of stuff, then we would need to square both sides of the equation. If, on the other hand, it was a cube root, well, then we would need to cube both sides of the equation. And of course, same idea, if it's a fourth root, raise both sides of the equation to a fourth power, and so on. And that's because if you have a square root and you square it, that gets rid of the square root. If you have a cube root and you cube it, that gets rid of the cube root. Now, you essentially just have to keep carrying out this process, isolate if there's any roots left, isolate them, raise both sides of the equation to whatever the appropriate power is, and then continue till you don't have any more roots left. And then once you don't, then you can now solve the equation. There is one big caution that I want to make here, which is that if you're solving a radical equation, and if you at some point square both sides or raise both sides of the equation to a fourth power or a sixth power, anytime you're solving a radical equation where there are even roots, so square roots, fourth roots, sixth roots, it's possible that this procedure that we're talking about using will create what are called extraneous solutions. These would be values of x that we might solve and find, but which don't satisfy the original equation. So I will say here that although it's nice to check your solutions for most equations, it's a good idea to if you have some spare time. In the case of a radical equation, it's mandatory. If you have even roots, you must check your solutions, and that's part of the work that I want to see you do when you're solving your problem. I also want to see you showing me you checking your solutions. And so we'll see a bunch of examples about that going forward. Start with the first problem. So here we've got only one root to worry about, just that 10x minus 10 minus 3x inside that square root. So I'll start off by first isolating the root. So moving the 2x to the other side, and then I will square both sides of the equation. And so that's our warning to ourselves. If you're ever raising both sides of the equation to an even power, squaring fourth power, sixth power, that's a place where you're going to need to remind yourself that you need to check your solutions when you get to the very end. So when I square the square root of 10 minus 3x, the root is gone. When I square 2x squared, that gives me 4x squared. I don't have any more radicals left, so I just have a nice quadratic equation that I can solve however I like. So you can solve this either by factoring, or you can solve this by using the quadratic formula, whichever you prefer. I'll do it by factoring. I'd be looking for numbers that multiply together to give me negative 40, 10 times negative, 4 times negative 10 rather, and things that add up to positive 3. And the numbers that multiply to negative 40 and add up to positive 3, that would be positive 8 and negative 5. And then just finishing off my factoring by grouping. 10 times negative 10 is 20. 10 times negative 10 is 40. 20 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 times negative 10 is So 4x is factored out, leaving x plus 2 behind. I factor out a minus 5, leaving x plus 2 behind. X plus 2 comes out as a common factor for both, leaving 4x minus 5. And now we can say what our solutions are. We come up with either that x plus 2 is 0, where x is negative 2, or 4x minus 5 is equal to 0, so x is 5/4. Now, if you stop here and just say my solutions are negative 2 and 5/4, that's incorrect, because as we'll see, there actually are not two solutions to the original equation. There's only one solution to the original equation, as we'll see in just a moment. So what I expect to see for this kind of a problem is that once you've solved and you've found out what the values of x are, you will need to now go back and check your solutions in the original equation. Remember, the reason we're going back to the original equation and not to the nicer quadratic line, the quadratic is what told us we had two solutions, negative 2 and 5/4. But the quadratic was not our original equation. We're not looking for solutions to that quadratic. We're looking for solutions to the original radical equation, which means we're going to need to substitute in our values into the original equation to check to see if left side and right side are equal to each other. So what I expect to see when you've got a radical equation and you've solved it, I expect to see you checking the solutions, and I expect to see you showing me you checking the solutions. So I'm going to start off with checking x being 5/4. And to show checking the solution, I need to show me putting 5/4 into the left side of the equation and into the right side of the equation, and seeing whether left side and right side are equal to each other. So what I'll do now is simplify. On my left side of the equation, putting in 5/4 for x, that gives me square root of 10 minus 3 times 5/4, which, using my calculator, I find that that's 25/4. 2 times 5/4, that's 5/2. And now I can see that I've got square root of 25/4, which is square root of 25 over square root of 4. And now I really have 5/2 minus 5/2, which is equal to 0. The right side of my equation is 0. So that means left side of the equation and the right side of the equation are indeed equal to each other. So 5/4 is a solution. That one works. Now let's check negative 2. So again, we'll be putting in our value for x into the left side of the equation. And seeing if it makes it equal to the right side of the equation. So here we'll have square root of 16 plus 4. That's 4 plus 4, or 8. The right side of the equation is still 0. And so my left side and my right side are not equal to each other, which means that we're going to reject x being negative 2. So that means that this equation, the one that we started with, has only one value for x in its solution set. The only value of x that solves the original equation is 5/4. So, like I said before, any time where we have to square both sides of an equation or raise both sides of an equation to an even power, that's something where this sort of work, showing you checking the solutions, is mandatory. And that's what I expect to see. I don't want to just see you saying that you checked 5/4 and I just have to trust that it worked out. I want to see you actually checking the solutions and showing that they work. Now, that's again only required in the case where we've got even powers. Odd powers, on the other hand, we don't get extraneous solutions for those. And the reason for that, of course, is, as you know, with an even power, even powers of negative, even roots of negative numbers aren't real numbers, but odd roots of even numbers, those are real numbers. So we don't have quite the same concern when it comes to odd powers that we do when it comes to even powers. So here I've got cube root of 3x minus 1 plus 2 is equal to 0. So I'll isolate the radical. Cube root of 3x plus 1 equals to negative 2. Since it's a cube root, I'll cube both sides of the equation. So on the left side, the root is now gone. And on the right side, negative 2 cubed, that's negative 8. And now at that point, it's just a matter of doing a little quick algebra to solve for x. And for this, if you want to check the solutions, you certainly can. You can check to see whether, if you put in negative 3 on the left side, does it make the left side and the right side of the equation equal to each other? But I don't have to do my checking of the solutions for this one because, again, we didn't raise both sides of the equation to an even power. We raised both sides to an odd power. All right, let's do one last one here. And this is one where it's a little bit more involved because we've got not just one radical, we've got two of them. So what I'm going to do is isolate one of the radicals. And what I'm going to do, just to make my life easier, I'm going to take this one, the negative root of x plus 3, and I'll move that to the other side of the equation. So I'll have on the left side 2 plus root of x minus 7. And on the right side, I'll have root of x plus 3. And I'm going to get rid of my roots by squaring both sides. And this will get rid of the root on the right side of the equation, but it won't get rid of all the roots on the left side, because remember that when I say 2 plus that root squared, I really mean 2 plus the root times 2 plus the root, and that means you would have 2 times 2, 2 times the root times 2, and the root times the root. So you'll still have some square roots left lying around on the left side of the equation. So when I simplify what's on the left side after I square both sides, I'll have 4 plus 4 times root of x minus 7 plus x minus 7. Okay, so now what I'll do is I'm going to take everybody that's not a root and move it to the other side of the equation. So the 4 root of x minus 7, I'll leave that lying around over here on the left side. And the 4 and the x and the minus 7, I'm going to move that to the other side. And when I do that and simplify what's on the right side of the equation, it simplifies down to just giving me 6. So now I've basically just need to repeat the process. I'm going to need to square both sides. So on the right side I'll have 36, and on the left side I'll have 4 squared times x minus 7. And now I just need to solve for x. 16 times x, 16 times 7, and I solve and I find that x is 148 over 16, which is same thing as 37 quarters. There we go. Now, you might feel tempted at this point to just move on to the next problem and say, great, we found our solution and that's that. But even though we only found one solution here, there's still not a guarantee that that would solve the original equation. This is what I mean about we definitely need to check our solutions. It's possible that you could start with an equation, find one value for x, and then it turns out that this value for x does not solve the original equation. It might be a possibility that the original equation actually has no solutions. So we can't just assume that since we only found one value that it must solve the original equation. It's still mandatory. We still must check our solutions. So let's check, and we're going to check our value of 37 quarters by putting in 37 quarters into the left side of the equation. And this is, again, a great place for you to use your calculator to simplify things for you. 37 quarters plus 3, that's the same thing as 49 over 4. 37 quarters minus 7, that's the same thing as 9 over 4. And so we'd have 2 minus the square root of 49 over the square root of 4 plus the square root of 9 over the square root of 4. And if I were to add that up using my calculator, 2 minus 7 halves plus 3 halves, that's equal to 0. And on the right side of my equation, the original equation, the right side was originally 0, and that means that the left side and right side are indeed equal to each other. So now we can feel confident and say that yes, our solution set will contain that one value, 37 quarters.